My name's Professor Tim Denison. I'm with the Department of Engineering Science at the University of Oxford. I came to Oxford after about 20 years in industry working on semiconductors and medical devices. And it's my pleasure to talk today about neurotechnology platforms and the role that CorTec has in building out the next generation of devices and new therapies. So if we think about the history of neuromodulation, brain stimulation in particular, platforms have always been an implicit part of it. The first generation of devices that came about, particularly for essential tremor and Parkinson's disease, were really modifications of cardiac pacemaking technology. So historically, the lead was actually routed up through the neck and then placed in a specific location in the brain by a stereotactic neurosurgeon. What's interesting is that those lead locations were determined and were replacing what was historically an RF lesion. So there was a direct understanding of where the lead should be placed, and then adjustments were made to the stimulator through an external telemetry system. But this was an electronic platform really derived from cardiac pacemaking technology. And one thing I want to emphasize is that the location and the understanding where to place the lead was really predicated in many cases on what was an existing RF lesion target. And why that's important is that when we think about new generations of therapies, where the understanding may not be so clear of exactly where to place the electrode and the actions to take, we really need a next generation of platform neuroscience technologies to help unlock those questions and understand how we should optimize therapies in the future. So examples of where research platforms are exploring new therapies and kind of motivate the need for the brain interchange are arising out of the Brain Initiative. So some of the highlights that I've seen and helped to participate in include, say, improving essential tremor devices. So Aisha Gundez and Kelly Foote at the University of Florida are exploring how cortical and subcortical electrodes can sense the intentions of patients and then use that to dynamically titrate the thalamic stimulation. In the short term, they're looking to improve the battery lifetime, but longer term, through this brain-computer interface, able to measure the intentions of the patient. They might be able to do a better job of adapting therapy to better improve symptoms while avoiding side effects such as speech dysarthria or paresthesias. A similar approach is being explored by Dr. Phil Starr at the University of California in San Francisco, where once again he has bilateral cortical electrodes and two bilateral subcortical electrodes down in the basal ganglia. And then with Parkinson's patients, he can explore the interplay between cortical, subcortical networks, sensing activity as well as stimulating, and through his algorithms look to refine both how stimulation acts to treat Parkinson's symptoms, but also how he can optimize the care of pharmacological agents such as dopamine, as well as stimulation over the course of the day. So once again, emphasizing this notion of not just one location, but the recognition that many brain disorders are actually issues within the overall network. And can we actually create research platforms that tap into the broader network in the brain, and then sensing the abnormalities and applying distributed stimulation, perhaps be able to steer the brain network into a more neurotypical state. Examples that get farther out from established therapies, say movement disorders, and look to neuropsych and epilepsy, are being explored, say, by Dr. Helen Mayberg at Mount Sinai, Wayne Goodman at Baylor, once again applying distributed neural technologies to understand how brain networks are involved in disorders such as obsessive compulsive disorder, as well as depression, and the role that sensing and algorithms can play to optimize therapeutic stimulation. Epilepsy in particular is very exciting because of the nature of the distributed disorder, the fact that we can look for these putative biomarkers and use them to adapt stimulation and try to tap into the natural rhythmicity of the brain and adapt algorithms in real time that can optimize both the suppression of a seizure as it exists. But more excitingly, can we actually predict when the seizures might occur in the future and take appropriate action, either to warn the patient that there is an imminent seizure, or better yet, apply a stimulation pattern that helps to avoid the seizure ultimately coming out. These are just a few of the exciting examples of research that's currently ongoing. However, the platform itself is predicated on existing technologies used in commercial therapies, and this can kind of be a limitation. And so the exciting part is to work on a next generation platform that is uncoupled from some of the historical limitations and really pushes the capabilities of sensing, stimulation, and algorithm capability into the next generation of potential research instrumentation and therapy development. And that is the key advantage that the brain interchange will bring to this space. So by more than doubling the number of electrodes, greatly expanding the sensing and algorithm capabilities, as well as the stimulation control, we can really start to take what has historically been a promising field and actively bring it forward into the next generation of translational research. So if we think about the role of platforms historically in neuromodulation, we can actually learn from the past and use that to help to inform what the future might be. So with the base deep brain stimulation device, initially going in for essential tremor, researchers, clinicians could apply this technology and then start to push into new areas, such as moving the electrode location for Parkinson's disease, fine-tuning the therapy over time, and then also evolving into new indications such as dystonia, obsessive compulsive disorder, as well as epilepsy. Now, one key consideration for a platform is both the strengths and opportunities it brings, but also its limitations. And so many of the historical platforms that were used to bring this trajectory through movement disorders and start to explore areas such as epilepsy, while powerful from their base stimulation capabilities, were still quite limiting in their sensing and their algorithm capabilities. And a caution that we have to apply in a platform is trying to overextend it beyond what its latent capabilities might provide. And that's what really motivates the next generation of technologies. So when we think about the role of the brain interchange system, it brings multiple unique features that are really important for the next generation therapies. Most importantly, from my perspective, is the ability to sense from multiple electrode locations 24 hours a day, 7 days a week. What this allows us to do is really capture the deep neuroscience from multiple neural targets, understand how stimulation perturbations, as well as pharmaceutical interventions, correlate with symptoms and side effects, and then with the digital platform technology, the ability to fine-tune and prototype next-generation algorithms that look to optimize the care of patients, minimizing their symptoms, trying to avoid side effects. And it's this deep capability of multiple electrodes, a bidirectional interface across multiple networks in the brain that's particularly exciting for the next generation of therapy development. Another key differentiator of the brain interchange system is its modularity. So one of the issues and opportunities that we have in the future is the unknowns about what exactly is the proper neural interface to apply, where should those locations be. So with the approach of modularity in the design of the neural interface and the ability to plug in multiple electrodes into a common brain interchange system, this really gives researchers the opportunity to explore without predetermining by their choice of electrode exactly where and how they're going to interface to the nervous system.